Okay, finally back after our Mardi Gras break. I'm sorry that I kind of got sick over the Mardi Gras break, so I didn't have as much fun as maybe you all did. So I kind of spent most of my time in bed recovering. So it wasn't until today where I'm like, okay, let me see where we last left off. I forgot that I hadn't published the videos for lectures 7 and 8 after we had our last set of lectures before our before break had started. So those are now published online. So if you go to the playlist, you'll see that lecture 7 and lecture 8 is available on the playlist. And you should also see that the GitHub repo is also updated. The README should reflect the contents of all the lectures we've had up until this point. So all the source code files that we've covered inside of our class from lectures 1 through 8 would be available to you. Let's see, other things I need to go ahead and mention. The lab one that I said that I was going to make live is indeed live. So you now have access to the data lab. I tentatively have that dated as March 1st deadline, but I'm flexible with that since we're still kind of covering the concepts related to data lab. Now, just like the intro lab, all the lab work and just in addition to the to-do app as well, everything I encourage you to do in group projects. So if you've already found a group that works for you, you could work on the data lab in the same group. Or if you didn't find a group that worked well for you, you can go find a new group, right? So you can mix and match however you want. This week, I will provide details for what the midterm exam will be. I'll give you clues to that right now. I'll formalize it and give you the actual rubric, but I'll kind of announce what it is so you can start thinking about it. So what the midterm exam is going to be is effectively going to be a group-based project, a group-based presentation, where from a collection of different shell applications, you select one of them and you do a deep dive, where just like I go ahead and do presentations over the course of the lectures to show you how C code works, you're going to show a popular shell application, something like SSH, something like grep, so that this way, all of you will get some topical exposure to popular shell applications, and at least each group will get a very deep experience having to present on it. So what I'll do is I'll actually present a collection. And of course, once one's been selected, no one else can select that so that we have a good diverse pool. And if there's one that's not on the list, just check with me to make sure it's okay. But it's possible to do a presentation on a shell application that I might not provide if you're interested in it as such. So that just gives you an idea of where we're going to go with the midterm and kind of like the value we'll have to the class as a whole. Because one of my motivations behind this class is I want you to be familiar with C coding. I want you to be more familiar with being able to use the shell as an environment to be able to not just understand how our processes run, how our applications run, but how you can use it as an environment in itself. Because there's applications you can run from the shell that allows you to do everything that you can do in a windowed application, including authoring your text files, compiling your text files, and executing your executable files. And of course, the advantage of that, the reason why it behooves you as a collective set of students who are majoring in computer science to have that kind of expertise, to have that kind of knowledge at the shell level, is because you're not always guaranteed a windowed application for you to be able to either read files, access files, edit files, or run files. Think in particular in terms where you have to SSH, where you have to remote into what's called a headless server. A headless server means it does not display to a monitor. So the only way you can communicate with it is through networking to using some other computer system that you're interfacing through a command line interface. It doesn't create windowed applications. And so if you're going to be a proficient developer, it's important you develop that skill set. where you don't necessarily need to have a monitor. You don't necessarily need to have a windowed application to be able to access the file system, be able to edit and read files, and be able to execute applications. And so one way we can all get proficient at that is if we could kind of all touch some of the technologies that are available at the shell, and we can kind of share those experiences amongst each other. Also, I think it's a lot more fun doing peer-to-peer instruction things as opposed to me constantly come up here and showing you things, because I think that gets boring. I know when I'm on the flip side of that as a student, I get really bored just listening to an instructor kind of drone on every lecture again and again. So I also want to open up like what we had probably pretty soon. We'll also have some more like in-person group sessions like we did with the when we were doing the to-do list. And so that brings me to the kind of last update. Over the course of maybe this week and next week, I want to start catching up on just making sure that I have the opportunity to evaluate everybody's grades. I will state though, I'm on a really strict deadline right now, so I don't have a whole lot of time. So if I can't do it this week, I'm going to have a lot more time next week. I have a tight March 1st deadline I have to meet. And then after then, for trying to get my dissertation in, after that, my availability should open up tremendously. Okay, let's see. I think I have some chats here. Should I make an appointment to go over the to-do app with you? Yes. So when it comes time to trying to make appointments, let me try to find out when my availability is going to be, and we're going to schedule everything through the Discord application. That is the de facto communication venue that I want to try to go ahead and use. Excellent. Okay, so I guess before we start on today's lecture, so I know it's going back not last week, but the week before then, we had talked about how we can represent all of our data in the form of binary sequences, and how effectively everything then, once we take whatever it is, whether it is text-based data, whether it's image-based data, whether it's sound-based data, we all find a numerical representation to encode that. And then once we have a numerical representation, we can go ahead and then encode it in a binary sequence. And so that's how we store information inside of a computer system. And so if you think about that, it's pretty radical. It's pretty impressive on how much information, how many concepts we can map into the world of math, right? And so I can't stress this enough. Just like we have a very powerful capability as humans to take a set of glyphs, like characters, and build a language around that, map a unique set of characters to then match into a concept of something, do concept formations. You could do the exact same thing with the glyphs in mathematics and then build concepts around that. And so when people say math and language are symmetrical, where there's a relationship, where you can express things mathematically the same way you can express things linguistically, that's very true. I think the biggest deficiency we have in a lot of our math classes is you're not taught to do concept formation using quantifiable values like you are taught to do in a lot of the more natural language classes and English classes, for instance, composition classes, literature classes, where you go through, you read, you learn to parse, you learn to kind of separate the concepts of what is inside that string of text and create a model inside of your mind. And then you can re-express the model that you have in your mind in terms of verbs and nouns and adverbs, right? And so one thing that I think really is the biggest kind of affordance to you as a computer science student is that you're kind of forced into learning how to use numbers, how to use effectively the math, the backbone of math, for concept formation, for learning how to start modeling the world around you in the form of numerical representations. And so initially, this is really confusing and this can be very frustrating, right? And so I know in 1583, We slowly motivate the concept of an object. But it's incredible the amount of context we can encapsulate with an object when you break it down, the fundamental data types that are available to you in the higher level languages, like numbers or text or Boolean values, right? At the end of the day, are just encoded as numerical values. It's just whether it is treated as a numerical value or as a set of enumerated values. That's usually what text is used for, like labels, so that can be categorized, or whether your numerical value represents something that's either true or false in the case of Boolean values. So we left off, I think, our last lecture after motivating the idea that all data inside of our computer systems, which is incredibly diverse and every day is getting more and more impressive, at the end of the day is numerical. So the thing we want to focus on and ensure everyone has a strong understanding of is how do we represent our numbers inside of the system? How do we map numerical concepts to our binary sequences? And of course, there's one of two ways we can do that, right? So when we were looking at binary sequences earlier, when you learn how to count in binary, you're using effectively, we're talking about the unsigned numbers, which would include only the non-negative numbers. And of course, there's an alternative mechanism by which we can go ahead and encode our binary sequences to represent numbers, which is a 2's complement. Now, am I correct in assuming that in assembly, you've covered these two different numerical encodings? Excellent. So I can kind of fly through this for the most part, but I'll slow down at places just to go ahead and get a pulse on it. So so obviously we have our two different integer representations. And of course, the consequence of this is that they're going to have different ranges. That makes sense, right? Because the thing that limits us in terms of our binary sequences is, as we know, there's a finite number of addressable spaces inside of a computer system. And so we get to decide when we define a data type, we can have multiple data types that all represent, let's say, integral data. So when I say integral data, you can think of that as discrete countable values. That's like 0, 1, 2, 3, 4, or it could be -3, -2, -1, 0, 1, 2, 3, 4, right? What it doesn't include is anything with a fractional component. That's a whole different encoding scheme that we'll look at later, probably next class. Okay, with that said, we can have the same set of values, but we want to define them across different number of byte encodings. So of course, the smallest is car. Car is 1 byte. We already talked about that, but effectively it's an integer type. It's an integral type. Then we actually have our short, which is usually 2 bytes. We have our longs, which is, we have our ints, which is usually 4 bytes, and our longs, which is usually 8 bytes. So, but the things they represent are the same. It's just the number of different encodings you have is going to be more so. So we know that when we start looking at the sizes inside of C, when we start looking at our integral types, our integer values, our non-fractional values, one of the things we want to pay attention to is the actual size, and that's the binary size. The other thing we want to consider is what is the number set that's included in that. So when we talk about integral data types, we have the integral data types, which is all the integer values, right? Negative and positive, but a subset of that, and probably the type that you first start learning to count when you're a child, is going to be the whole set, which is going to be your, which is going to be the non-negative values, starting at 0 and then counting up. Because usually, I don't remember, what grade did they finally teach you that negative values is a thing? Is that 3rd grade? Second grade? I don't remember. It's been a long time. But when you first start counting, usually you start at the 0 value, right? And then you go 1, 2, 3, 4, 5, which makes a lot of sense. Okay, so with that said, let's take a quick look at the different representations of integers then. So if you allow for signed values, then you're clearly going to, let me rephrase this. You have a set number of combinations, of permutations is the better word, of a binary string. So let's say that the size of your binary string is a single byte. That means you have 8 characters, 8 bits that you can use to encode each unique value, right? And so clearly, if you decide to go unsigned, that means all positive or non-negative values, because you can also have 0, and 0 is neither negative or positive. So if you go with non-negative values, you can start at 0 and then encode the maximum number of values that you would have, which would be 256. It would be 2 to the power of 8, right? So when you first learn how to count in binary, that's actually the encoding scheme you learn, right? An unsigned encoding scheme where all zeros is 0, and then all zeros except for the least significant bit is 1, and so forth, right? Now, if you want to include signed values, clearly you're going to cut your range in half. You want your 0 to be at the center point, and approximately half of your values are going to be negative, and the other half are going to be positive. So clearly, with our minimum value, we're going to have, like, if it was 256 with unsigned, it's going to be minus 128 for signed, and then 127 on the positive side, because again, we have to include 0 as one of our non-negative numbers. So half of our domain would go towards negative numbers. The other would be non-negative numbers, which would be 0 and the positive values. Okay, let's take a look at the some sample code this really quick. So we can either look at a table. I always like to look at the output from a from code, because I just think that's the better way. Let's take a look at this. What do we have here? It's 0, 0. Here we go. So let's take a look at our num ranges. So just looking at the simple code, all I'm doing here is I'm going to import my standard input and output header. I'm going to include this limits.h, which gives me access to my limits of my integer values. So now, because of that, I can get notice I'm accessing some predefined values here that I didn't define in the code. I import it. So for instance, this is my signed character minimal value, my signed character, this is my min. So this is my signed character min. The reason why I'm doing it twice is that inside my print statement, I want to show you the decimal representation, but then I want to match it to the hexadecimal representation as well, so that you can see the encoding for the min and the max for each of the various sized integral data types. That's going to be character in both types of sets, the signed and unsigned set, the shorts, the ints, the longs, and the double longs, the long longs. And of course, we don't have to memorize what these are because we're going to import the limits and just call those constant values. Okay, so let's go over here and see exactly. Clear that. Okay, so let's do GCC. Let's compile this code. And let's give it an output name of ranges. Okay. So when we look at this, we can see, okay, for our signed characters, min and max, again, very obvious, minus 128 to 127. And again, by doing this, we can then see how they're actually encoded. And so if you're familiar with two's complement, which we're going to go through more today, usually your most significant bit is used as your sign bit, which allows us to effectively half the space. So if it starts with a 1, then it's going to translate into a negative value. If it starts with a 0, and notice here, it's going to be the value of here kind of front loaded these, it would have been nice to, I'll have to modify this code so it fits based off of the byte size as well. So it only prints out the first two, the first two hexadecimal values, which represents your encoding for a character. But here you can see 7 and F, the leading most significant value then is going to be a 0 on a 7. So here, this is one way. This is actually showing the exact same values we have inside of that table, but this gives you some source code, so you can actually always inspect this yourself. Or you can always actually, instead of having to memorize that table, you can just import a library and access whatever the max or min value inside of any data type at any given time. And of course, if there's any questions, just go ahead and drop that in the chat, or if you're in class, ask. Okay, so let's talk about the unsigned encodings. So we already talked about how we can express our binary sequences in the form of bit vectors. It's a very popular way of encoding our binary strings. So there's one of two notations we can use to denote a vector inside of mathematics. You can either express an entire vector collectively by a label, an identifier, let's say X, and then you can put an arrow on top of it to say this is a vector space. Or you can show the individual elements contained inside of the vector. Here we'll use a box notation where we are going to represent our binary sequence where the most significant bit will be the first one, the one at the far left, I should say, and moving towards the right will be our least significant bit. Here you can see the position identifier for each of the individual bits in this representation. Okay, so then if I wanted to create a function that allows me to take a binary string, a vector, so my vector, again, using the notation of X with an arrow, can also be thought of as a binary string, a sequence of ones or zeros. So suppose I wanted to create a function called B to U that operates off of some W. The idea behind this function is it will translate my binary string into an unsigned value. So the mathematical expression that we use in order to translate our integer value into a binary string in which we can then store into our computer system would be this. Is everyone familiar with this kind of mathematical notation? So the basic idea here is B2U is essentially like a function name. It's short for binary to unsigned. The sub W illustrates that there's a dependency on knowing what the width of our binary string is. So W is going to be the width of the vector. The thing that's actually getting passed in here is the binary string. So X is our binary string. So the way we can implement that is using sigma summation, which means that it's effectively like a for loop in computer science. So here we take this term and we sum it to itself, starting where I is equal to 0 until we meet the width of our binary string minus 1. So that tells us the initial indexing position, and then it tells us what the terminating condition is for our for loop. This is the original for loops in math, right? Before we started to map them into programming languages. Okay, then what we're essentially doing here is we're taking the index value, so the sub I means that inside of our vector, we have a number of elements. We're going to access at a per element basis, starting at index 0 all the way until width minus 1, right? Because our countable values go from 0 to however many digits you have. So this is either going to be a 0 or a 1, right? Because it's binary. So, and then we're going to multiply that. So clearly it's a 0. We're multiplying it with whatever this is, but then that just zeroes out. So it doesn't matter. So this only really matters on the instances where inside of our binary sequence, it's a 1. So if it is a 1, then this is actually going to matter, or inside of my binary sequence, then I'll multiply that to 2 to the power of I. And because the idea behind that is that, recall, in a binary sequence, each digit you move to the left, to the most significant bit, is a multiplier of 2. It's an exponential value. So 2 to the 0 is the least significant bit. 2 to the 1 would be 2. That's going to be the next significant bit. 2 to the 2, 2 to the 3, 2 to the 4 is allowing me to go ahead and move across the binary sequence a digit at a time. Does that make sense? No, that's effectively saying we're going to define as. It's not an equivalency of, if that makes sense. But for all intents and purposes, we can think of this as we will define our function as this sigma summation.
Are these slides on Discord?
They should be. These are based off of the slides I had. I have been updating them slightly though. So what I'll do is I'll save them actually as PDFs, and I'll actually start posting them into the GitHub repo. So what I'll start doing is I'll create a new folder in the GitHub repo that now also has your labs and has all the sample code. I'm trying to aggregate out all of the resources in one space, so there's a one-stop shop for everyone. And the GitHub repo is actually linked inside the comments inside of the description of every video. So at any time, if you can't find, it should also be linked in the Discord as well. You should be able to find it lots of different places. Okay, actually, let's take a look at what this actually looks like. So now that you see the mathematical notation for this, let's examine what this looks like in the form of actual executable code. So I'll quit out of this. Okay, so let's go to here. Okay, so, and let's clear out of this. And let me compile it, and then we'll walk through the code. So this is going to be 0, 1, and then dash 0, and then let's call this B to U. That's binary string to unsigned. Excellent. Okay, quick. So I'm going to start with the main function, and then that's going to motivate on how we're going to call the actual function we care about, which is going to be this BTU, which is the exact same implementation-wise of what we just saw in the mathematical formatting. So inside of our main function here, we're going to create a binary string, right? So a character pointer that's going to have 8 bits that are either zeros or ones, and we'll do another 2 just so we can compare. Then notice I'm going to get the actual value. So the idea is we want to translate from a binary sequence into an unsigned integer value. So we're going to use that logic. So notice there's going to be 2 parameters we're going to pass into BTU, which is the same parameters that we saw in the mathematical notation. It was our vector. So our vector is just a sequence of values. It's like a list, ordered list. And we also need to give it the width of our vector. That's that W. Okay, so given that, let's take a look at our BTU. Notice we're actually using unsigned for everything to harden our requirements, because that's the entire point. This is a binary string to unsigned value. So we're going to return an unsigned integer. We're going to require a character string, which is going to represent our binary sequence. We're going to pass in the length of our binary sequence. We're going to start our integer value at 0. Now we're going to do the sigma summation, which is effectively a for loop. We're going to start our for loop at 0. So I is 0, just like the mathematical notation had. And we're going to go until we hit the length. This is an equivalent way of being inclusive, where we say length minus 1. Which is what the mathematical notation does. This is a more common way in your science, but you get the same idea, right? So one way to at least separate the sigma notation is sigma notation is inclusive of both the top and the bottom, not exclusive. Okay, so we'll go for the length, and then we will increment for each iteration, which is actually the same thing that's happening with sigma summation, if I didn't state that already. Lots of similarities between sigma summation and for loops. Okay, so then once we're in there, we're going to go ahead and we're going to take a shortcut. We're going to check to see if it's a 1, but we don't have to do that. We can do the same thing that's happening in the mathematical notation, where we just do it with every value and zero it out by using a multiplicative property, right? But we won't bother doing that. I might refactor to do that, but in this instance, we'll only perform the action when it's 1. See, in this instance here, we're performing it for every value, but it filters the 0 values out because you're multiplying by 0, which produces a value of 0, which means you're adding 0 for that term, which isn't producing any change. It's not making a change of state to your summation, right? Everyone's okay. So then on those instances, we have 1. That's when we're actually changing the sum. So here we will take our value, which starts at 0, and we will add to it. And so this is one of the beautiful things about these binary operations we learned last class or the class before. This is a way of producing a power of 2 on a binary sequence using the shift. So when you shift a binary sequence by X number of units, it's like shifting it from 2 to the power of 0 to 2 to the power of 1 to 2 to the power of 2 to 2 to the power of 3. So here we want to shift a 1 value. And so if I put U, uppercase U after a 1, that is a literal integral unsigned value. So 1 on its own is a signed integer value. 1U is a way of ensuring that that gets cast as an unsigned integer. The only reason why I'm doing that is to harden our requirements inside of this code. So I want to illustrate to you that just like you could say, for instance, add an F to a fractional number so that it's treated as a floating point number, but the default value is a double, we can enforce unsignedness onto one of our literal integer values to be unsigned. We do this just to ensure that the shift is done as a logical shift and not as a sign-based shift, which we shouldn't have an issue since we're shifting this direction anyway, but you always want to be careful and see. And we're going to shift a number of values based off of what the exponential placement is inside of our binary sequence. So again, we started 0, 1, 2. So you're thinking that what we're shifting by here is effectively this value here, this 2 to the power of I, which in our case is going to be 0, 1, 2, 3, 4, 5, 6, 7, up to 7. Okay, once I do that, I will have added to my value the 2's place every time a 1 is in my sequence at that position. So then I'll take my final sum and I'll return that. So I want to ask, does seeing the source code here make this easier to understand? Okay, perfect. This takes a lot of time to show both. And so then let's go ahead and test this out. So I have 2 binary strings. Let's pass these 2 binary strings into this function that we've implemented based off the mathematical definition to see exactly how that goes and maps out. So here we go. And so here we can see my unsigned integer value of this binary string will then result in being able to encode the value of 99. Or my binary string here results in me being able to encode the unsigned value of 149. And again, this is using the same principles that you might have learned to use counting in binary. These are the default counting rules using unsigned values. But here you can see how we can actually create a C program that maps our binary strings directly into integer representations, unsigned integer representations. In fact, this is how our underlying system does it. Okay, so now if I were to use the representation of the book, this is how the book tries to explain the same kind of concept. So I think it's nice to have a mathematical approach. It's nice to have a programmer's approach because we've all learned how to program. So there's a value in seeing the math mapped to a to code, but also we have a visual approach, which I know for those visual learners out there, this might even be able to add on to the code that we've looked at and to the math that we've looked at. So just to harden this, one way we can think of each of the positional values inside of our binary sequence, inside of our bit vectors, is having a certain amount of magnitude towards the full sum that represents the integer value. So again, we have that idea of most significant value versus least significant value. The least significant value is going to contribute less to the integer representation than the most significant value. And the amount of value it provides is based off of 2 to the power of whatever index value it is inside of our bit vector. So we can actually visually create these blocks that represent how much of a value each of these can go ahead and be a part of. So imagine here, for any value we can represent in a binary sequence, we created a block that represents one of the construction points, one of the building blocks of all of our integer values that we have. Then this would represent our 2 to the power of 0. That's just 1, right? Anything to the power of 0 is 1. 2 to the power of 1 is obviously 2. And then you can double that, and that's going to be 4. You can double that, and it's going to be 8. And obviously, one of the beautiful things about taking to the power of 2 is you're constantly doubling it in size. And then what we could do is we can create this number line that represents the actual integer sets of values. Here we're using a decimal representation, and you can see how we can map a binary sequence that says what block it includes. So again, if I have 0, 0, 0, 1, and if I just include that one size block, I can then map it to this value of 1 here. Let's say I want to make 5. Then that's going to require a block size of 4 and a block size of 1. You combine those together, that will produce 5. So visually, I can take this and this. And so in order to access those block sizes, I integrate it into my binary sequence. So do you see how, does this visualization help at all? And so this is actually the one that's given in the book to try to motivate this concept. And again, if I wanted to build 11, you could see I could use this block size of 8, this block size of 2, this block size of 1. And again, what we do is we're showing how we can pass that binary sequence into this function along with this width size. We can then show the actual summation between each of the independent values, what it resolves at, and how we then convert it into its representation, its integer-based representation. So suffice it to say, the least value in an unsigned value is 0, which is represented as all zeros in our binary string. Not the true with 2's complement, which we're going to get to. And our greatest value is when you have all ones. And in fact, the way that we can always find, based off of some arbitrary length of a binary string, what the max encodable value is, you can take 2 to the power of whatever the width of that string is. So say, for instance, this is 1, 2, 3, 4. We could take 2 to the power of 4 is what? That's 16. Subtract 1 by it, and that is going to be, because 0, 0, 0, 0, 1 encodings for the 0 value. So if we subtract 1, that's going to be the largest integer value that we can represent with that string. So if you ever want to know what your max value of an unsigned is, that's an easy way of doing it. And again, if we want to test that, we have the UMax.c, which is going to define this function. This function is based off of BTU, where we just pass all ones into our binary string. And so I don't know if let's go ahead and in here, just take a look at it. So Pretty simple. What we see here is we're going to create UMax, which instead of taking a binary string, just takes a width because we're looking for what the max encodable value is. And then we're just doing the same thing we've already seen. We're going to shift a one, or we're going to shift a one a number of times equal to the width value and subtract one from it. So if it was 4, right, it's going to be shift the 1 4 places. It's going to be in binary a 16, subtract 1, that's going to be 15. But the nice thing about this is it could be any arbitrary value. It's very easy and quick to be able to find the max encodable value. And we can test this out. Let me clear this. Let's take a look at the output. Now, what is this? Max, UMax. And you can see right here, yep, the UMax, the unsigned max value for 4 bits would be 15, which isn't just an integer value. Actually, this is a, well, yeah, it is, but if we didn't subtract by 1, the other interesting concept of this is it would also represent, it would just be 2 to the power of the width. That's the number of encodable values you have. So it lets you know what your dictionary size is, how many things you can encode uniquely with that number of bits. And of course, if this function is going to be useful for us to encode our binary strings into integer representation, it has to be a bijection. Does anyone remember what a bijection is in mathematics? So a bijection is a special type of function. So we know that in a function, you have the ability to map a value x to a value y. So it's usually inside of this representation where y can equal f of x, where f is a function that we pass x to. It resolves into a unique value for y. A bijection means that there's also an inverse function. Given that x equals the inverse function on y, that means there's a one-to-one mapping. That's super important, that our b to u function also has a corresponding u to b function. It would be otherwise, we have like a lossiness inside of our conversion. You don't want to be able to take a methodology of taking a binary string and representing it as an integer, but then not having the integer be able to resolve back into the original binary string. So any one of these definitions that we have that allows us to take binary strings and map them to values have to have an inverse function that allows us to take the value and remap it back into a binary sequence. And they have to be the same. And so that means we'd have a u to b. Let's take a look at what it would look like. Okay, let's just take a look at the main function really quick. So suppose that I have myself an unsigned integer value of 99. Suppose that I have a width of 8 for my binary string. Let's go ahead and create a binary string array, so a character array that we can translate our integer value in and then put the binary sequence into. And so when we go ahead and declare that space, notice for the purposes of strings, we're going to do whatever the width is plus 1, because we need to terminate our string with a null character in C, right? Then we're going to call our function u to b. U to b will take the integer value. It will take the width of the binary string we want to go ahead and encode into, because recall in C, we can have integer data that's in the form of chars, in the form of shorts or longs, or ints or longs, right? So in this instance, we could pass the width as 8 or 16 or 32 or 64. And then finally, the actual character pointer or the character array in which we'll then build our binary vector, our bit vector for our binary string. So here, again, this is going to be effectively a for loop. It's effectively the inverse of our B to U function. So notice, since it's kind of like an inverse, we're going to actually start from reverse side, right? We're going to start by building, we're going to do concatenation. So we're going to start at the width where we take whatever the width minus 1 is. And then we're going to go until we hit 0. So we're going to start at the most significant bit and then build to the least significant bit. And then here, we're going to use this bitwise operator where we'll take the value, and this is going to produce a mask for us. So remember that concept of masking we talked about? We're going to use the bitwise operator, so we mask all values except for the one space that we want to evaluate at this given time. And then we're either going to put a 0 or 1 inside that part of our binary string. And we're indexing into our binary string. And then when this is done, the very last position, we're going to add a null character to say, okay, this is now treated as text data, as a character string inside of C. And so if I go ahead and run this, actually, let me clear my output so we don't have old output there. And what is this? This is U to B. Then we can just run this. And we can see, based off that, we can easily take our bijective function, our inverse function, where we take the value of 99, and then we can represent it as the binary string for our unsigned integer representation. So again, this is just a way of motivating what the system's actually doing for us to translate between binary to integer values, unsigned integer values. Okay. Let's now look at 2's complement, the alternative encoding scheme that gives us the ability to actually encode negative values. So here, this allows us a very powerful concept of having a negative number, such as -5, where we didn't have that with the unsigned encoding scheme. But as we've already mentioned, it's going to have the number of positive values that we now have access to so that we can provide an encoding for those negative values. So for 2's complement, it can be defined mathematically where the most significant bit of our word, our binary word, is the sign bit, which is why it has the numbers too. The sign bit produces half the number of values you have if you were to build a tree of all of your encodable sequences. So if the root of your tree is either 0 or 1, half of those can go towards the positive encodings, the other half can go towards the negative encodings. The non-negative and negative is the more accurate term for that. So let's take a look at our vector. So we said our vector is this X with an arrow over it, and this is each of the individual bits inside of our bit vector. Then if we pass our bit vector into this function B to T for some width W, then the mathematical notation that we can then use for this is it would be minus X at W minus 1 times 2 to the W minus 1. So this is going to be our most significant bit. And then we're going to add to that the summation. So we have our most significant bit, and then we have the summation that looks very similar towards our unsigned set of values. So again, if we wanted to see what would that actually look like in terms of code, let's take a look. And so here we can see, let's start with the main function. So suppose that we have these binary strings, one that has the most significant bit at 0, one that has the most significant bit at 1. If we pass these into our B to T, where our first parameter is a binary string, and our second parameter is the width of the string we want to map into, that we want to read from, then we can take a look at our actual function. So here, this is the length, this is the binary string, this is the name. We start our value at 0. Then we can see we produce this for loop, which is our sigma summation. Inside our sigma summation, we're going to start at index 0 and go for the length of our binary string, incrementing along the way. If inside of our binary sequence, we have a 1, we're going to do something very similar here. But notice, according to the, there we go. So if our value is a 1, we're going to go ahead and do a subtraction from it, which is what we saw here, right? Otherwise, we're going to do a summation of it. And the summation or subtraction is all based off of this. This is actually doing a logical check on to see if the value of I is 0 and the length is greater than 1. And again, if we go ahead and actually test this out, and what was this? This was E to T. We could say that we have a positive value of 99 when our leading value is 0, whereas we have a negative value, minus 107, when our leading value is 1. So again, I think it's one thing to, did you all do something similar in assembly where you not only looked at the, did you look at the mathematics of this, or what was the process that these concepts were shown in assembly class? Was the mathematic notation shown? Was just the concept, was the process just shown of how to read this? Did you get a chance to see like these operations, how the operators are used to translate between your binary sequences and your numbers? Was it more like you just did it by hand? Yeah, that's what I kind of recall too going. That's why I think it's always valuable to also look at the foundational math and also look at the how the code. So remember, our systems are run in C. The reason why I'm actually showing you C code is this could be the same way that our underlying system also implements some of these concepts. Now, the actual assembly language can do all this stuff too, right? By just shifting the bits across. So you could see how at the assembly level, this would also work. So there's this one-to-one matching between the left shifts and the right shifts. Once we start talking about modifying binary strings, this has a one-to-one matching on what the hardware can do with the addressable space of sequences of bits. And again, we looked at code, we looked at math to represent this 2's complement. So let's also take a look at the visual representation. Again, this is taken straight from the book, where we have blue blocks that represent positive contributions to a sum, and gray blocks that represent a negative influence towards a sum. Because once we start talking about signed values, we can go in one of two directions, not just one. And so if your most significant bit is going to be represented as a negative value, that means that gray block is going to compete against all the blue blocks in that same grouping. So suppose that you had a width 4 binary string, then that's 1, 1, 1, 1. But the most significant one would be in gray, and that's the value of 8. The next one would be 4, the next one would be 2, and the next one would be 1, right? So if it's all 1s, then your gray block is going to be the 8, but minus 8, plus 4, plus 2, plus 1. So minus 8 plus 7 is minus 1, right? In fact, we can see that's exactly what we get here. So this is just the visualization that was used inside of the prior section to enhance it to show how we can get the encodable space to now deal with negative and positive numbers using this different sequence. And it's not one-to-one. Remember, there's an offset of 1, because what we're really talking about is negative versus non-negative. So if your most negative value is going to be -28, that means your most positive value will always be positive 127. So you can't just remove the sign bit, right? You might recall when you're doing the translation with this, you take the inversion of the number and add it by 1, right? Or subtract it by 1. Okay, so when the most significant bit is 0, yeah, we already know this. So when the most significant bit is 0, effectively the bit patterns are identical between our our 2's complement and our unsigned value. So the translation is the same. So the only time that you retranslate into a new value is if the most significant is 1. Does that make sense? So the encoding is the same for all positive values. The only time that we create a different value between our unsigned numbers and our signed numbers is if the leading value is a negative value, is a 1. Then that's when it matters whether we're using the 2's complement encoding scheme or we're using the unsigned integer or unsigned binary string encoding scheme. So let's take a look at least, let's see, what is this? Least value, greatest value, yes. This is just defining the actual TMin. So this is just showing, this is kind of we're seeing here that before, recall that on unsigned values, your greatest value was 2 to the power of w minus 1. To find the greatest positive value, your exponential value is actually going to be -1 inside of here, right? And that makes sense because for positive values, you have to omit the most significant bit when looking at 2's complement. Because if it is a 1, then it's a negative value. Of course, the most negative value would be pretty much similar to how we would compute the max value in unsigned, but we put a minus sign in front of it. And instead of being, again, w, it's -1, w as the exponent, and then -1 unit, it's w minus 1. It's half the encodable space, again. Very obvious, though. So let's move on. And of course, the motivation behind all this is taking bit vectors to represent our unique signed values, which we've spent a lot of time talking about. But in order for this to work, it has to be a bijective function. So clearly, if you have a mechanism that allows you to take a binary sequence and map it to a signed integer value, you have to be able to do the reverse. Can you take that integer value and map it back into a binary sequence, right? This is what allows us to start with 1, translate, store it in the machine, pull it from the machine, and retranslate it back into the value we think it is. And so to highlight that we can, in fact, do this to prove, I mean, clearly we all know this is possible because we see it all the time. But if we actually want to see the implementation of this, let's take a look at this. And so, yeah, oh, and by the way, let me do this as well. This might help as well. I'm going to load into Python here so you can kind of see this in real time. So inside Python, we can do these, some of these, so let's see here. So suppose I wanted to do 4 here. See, so you can see, if you want to play around with this, one of the issues with running code in C is that we have to compile and then we have to print it out to the console. One nice thing about a Rebel, like with Python, with interpreted language, is we can just run instruction at a time and kind of play around with it as if we're in a playground. So here you can see, this is, if I wanted to see how many encodable values of a binary string do I have by taking 1 and shifting it by 4 places, you'd see it's 16. So when we were looking before at what the max is, it would be it would be the same as this, and then minus 1 for the, nope. So it'd be like that, right? So again, this is just a way that this is the same in code arithmetically as what we would do inside of C, but you see I get my responses immediately. Okay, so just looking at this, you could see we would pass in our value, we would pass in the width of our binary string, our binary array, which is going to be character array, and then we're going to check to see if the value is greater than 0. Then we're going to want to set at 1 into our index 0. And then what we can do is we can then works with the positive magnitude value. Otherwise, we're going to set that to 0. Then after that, we're going to do our for loop. So this first part here that we're looking at is effectively the same that we saw in the mathematical notation. Remember, in mathematical notation, when we do 2's complement, we're dealing with the most significant bit, and we're adding a multiplicative property, and then we add the positive sum on top of that. So what that looks like in code is going to be whether we're starting with the negative value or whether we're starting with the value that's a value that's effectively going to be a positive value of 0. Effectively. Okay. Now let's see here. And so here we have some sample 67 minus 7. Let's just go ahead and run this. GCC, what is this? 0.5. And this is effectively just our bijection, our inverse function. So here's T to B. And let's run this, T to B. And so here we can see if I had the value of 67, it's going to, let's take a look at some of these concepts. Well, in 2's complement, the leading value should be 0, right? Because that's our sign bit. It is. This right here is 64, right? Because everything is in powers of 2. This is the value of 2. This is 1. I sum these together. Yeah, I can actually visually count that and see that that's going to be 67. And then here, this says it's minus 7. We can see, okay, this is the minus 1 here. So that's, and then this is going to be my value of 7. This is my sign bit. And then I can read that this is going to be minus 7,111, right? I saw this. And again, if I then wanted to compare my hexadecimal values between my unsigned and signed. So the idea between this is I want to show you that with the same encoding, the same binary sequence, depending on whether you're using a unsigned encoding versus a 2's complement encoding, you can actually resolve to different values. That's important, right? Because if you do some arithmetic operations in unsigned, and then you retranslate it into a signed value, that might give you a different number. This is why context matters. And of course, there's the ability for us to be able to convert between signed and unsigned through casting operations. So C allows us to cast signed and unsigned. And so what this should do is it should, well, so it's an interesting case, right? So if you cast, what do you think you're casting here? Between signed and unsigned in C. This is an important after effect you should consider. Because one of the powerful things about C is that we can change the context of a binary sequence. That's what casting means, right? So if something was originally authored as an unsigned sequence, it means one thing, but it can mean something entirely different in 2's complement as the same sequence. So when we cast, we're talking about keeping the binary string the same, but parsing the value using a different encoding scheme. So keep in mind, casting can be a dangerous operation. You think you might have one value and actually cast it into something else. That's the behavior of C. You should know that. That's one reason why we're going into such detail on the two integral data type encodings that we have access to. So say, for instance, I have this integer value. Now, by default, we don't have to say integers or signed or unsigned. The default value is signed, right? If we want it to be unsigned, we have to use unsigned. So suppose that I have this value minus 1, 2, 3, 4, 5, and then I want to cast that. So casting in C looks a lot like casting in Java, right? Where I take the data type, I put it between parentheses, and I apply that to the data. And what that's telling our C compiler to do is take whatever is inside this space, this addressable space, pull the binary sequence, and reinterpret it using this context. So it's not going to necessarily take the value and convert it into, so it's not going to take like minus 18 and turn into a positive 18. It'll just translate whatever that binary sequence is into a unsigned value. So let's see what happens here. So we're going to take this V, and then we're going to save it into UV, short for unsigned short V, and then we're going to print these two out. And so you're going to see my output is going to be different because it's going to use the choose encoding in the first instance, and it's going to use the unsigned encoding in the second instance. So suppose I wanted to go ahead and cast from unsigned to signed. Let's see how that might work. So suppose I go with the unsigned U, and here I'm going to use the max value. So this is on unsigned when all of my values are set to 1 for that particular sequence. And so this is a... And so here, suppose now on my unsigned, and I should probably feel like I should have an int in there, like a data type. Okay, so now suppose then I'm going to then cast into just int. So now that translates an unsigned int into a signed int. And so I'm going to save that into TU, short for 2's complement U, the encoding scheme, and we're going to print that out. And the actual output you're going to see is going to go from this massively high positive number to a -1. So casting is possible, but notice it's probably something you never want to do. But it can happen if you accidentally do math with different data types. Because what casting isn't always explicitly done, right? Sometimes casting is implicitly done. So keep that in mind. If, say, for instance, you had unsigned values, and if for any reason you subtract them in a way that can produce a negative value, sometimes C does something weird. So just pay attention to these. These are the little pitfalls that can happen with you in C that are worth knowing about. And it's the translation of our bit sequences and how we're constantly giving them context, but how context can be very different in the way that we encode the space. Anyway, you could see we can define what our ranges are, or the mathematical principles for defining our conversion between 2's complement to unsigned, but to do it in a way that's actually meaningful, where the limits don't necessarily break down. And so, well, maybe not meaningful, but we can see the onto relationship. We can see how we could translate one set of sequences in both ways. And let me show you that. So again, one of these instances shows you our B to U, our binary string to unsigned versus our B to T. So you can see these are the two mechanisms back to back where we can go ahead and do our encodable space. So with 2's complement, we have these gray blocks inside of our, that's light gray, right? And with the unsigned, we have these really dark gray blocks. So you can see we can kind of stack these to see what the offsets are for the same bit sequences. So actually, if I was to line these up, this is how our number range could map one on top of the other. I don't want to spend too much time with the conversions between this because I think you can see for the most part, all we're doing is translating values, unsigned values. The value here is that you can translate one unsigned value into the two's complement value without having to convert between the binary sequence. Sometimes that's valuable, sometimes that's not. I just want to illustrate that this is also a set of functions that we can do. And we'll actually pick up from here next lecture.